In the table of contents, you will go to experiments, followed by the IR folder. You will see here the in-class IR with class discussions and all the documents that you will need for your information. To begin with, your IR spectra ranges between 400 and 4,000 centimeter inverse. This is known as wave number. A wave number can also be represented by a 1 centimeter square box. How many waves can be accommodated in this 1 centimeter by 1 centimeter box? On the other hand, lower numbers indicate that lesser number of waves can be accommodated. Less number of waves means less energy is required. More number of waves means more energy is required. In general, when we look at IR spectra, towards the right-hand corner, you have all the single bonds. All the single bonds except the ones with hydrogens. The next region are double bonds. For example, C double bond O, C double bond C. The next region is for triple bonds. C triple bonded C, C triple bonded N, and so on and so forth. This particular region is for the bonds with hydrogen. If you look at all the electronegative elements and the hydrogen bonded to it, you will realize that these molecules can do hydrogen bonding, and hence they have a stronger interaction with other molecules, needing more energy for them to vibrate or to shake off. But before we reach these electronegative atoms, the most important carbon atoms bonded to hydrogens appear first. And then we see the more acidic and more electronegative atoms with hydrogens. Looking at our previous example, where we have a simple molecule and a more complicated molecule, but both of these molecules with same bond types. Let's assign them a number, the wave number, to them. When we are looking at the IR spectra, on the x-axis, we have the wave number, but on the y-axis, we usually have what is known as absorbance. How much energy is absorbed by that bond type? For example, if we assign CO 1000, C single bond C 700, sp3ch 2800 and OH 3300, we see at the baseline of 4000, no energy will be absorbed. We see at 3500, no energy is absorbed, but at 3300, we see a dip or absorbance of energy. Similarly, nothing at 3200, nothing at 3100, nothing at 3000. But at 2800, we again see a dip. You do not have to draw anything for all the wave numbers that we are not concerned with. And in a few minutes, I will let you know which those wave numbers are that you have to focus on and which of the others do you have to ignore. Similarly, we will then have a dip at 1000 and another dip or absorbance at 700. This is how and why we see the IR spectra. In here, I have listed all the sequences that you will need for solving your IR problems from structure and from spectra. We will now discuss how to use our IR packet for interpretation of the IR frequencies. If you look on your packet, these are the 5 regions and their respective frequency values that you need to memorize for this course. I also want to point out that your sp carbon-hydrogen bond belongs to region 1 but has been grouped with all the CH bonds. This frequency value in the bold numbers, this is what we are going to use for our class. For the first region, fortunately, all of the peaks do not appear as a single peak. They have different shapes depending on what bond type it is and what other molecules are attached to it. If you look at our OH peak type, this is the shape of the peak that we see. But if you see the OH which is attached to a carboxylic, the broadening of the peak is visible. When you have a simple OH, the presence of this indent or splicing right here identifies or distinguishes the OH connected to a simple carbon versus the OH connected to a carbonyl carbon. When you have a OH connected to a carbonyl carbon, your absorbance will be between 2500 and 3500, which spills or merges in region 2 also. Remember, OH is in region 1 and your CH bonds are in region 2. So we see a merger between region 1 and region 2 peaks. So if you look at the IR spectra of an alcohol, this is region 1, this is region 2, we will see that the OH appears and our sp3CH2 peaks appear as two separate peaks. You may also see them something like this, but this indent or splicing will be very evident to you. This splicing will be absent in the case of carboxylic acid peaks. Your primary amines and secondary amines, as well as tertiary amines, there are no NH bonds in tertiary amines and hence no absorbance in this region for tertiary amines, which will help you differentiate between tertiary amines and the other amines. The terminal alkyne has a icicle-like peak, like in here.